Hey Geometry, welcome to our last lesson in 8.4, Proportionality Theorems. So in this lesson we're going to be using the triangle proportionality theorem and its converse and some other proportionality theorems, two other proportionality theorems that we will learn about and see what they are about. So definitely proportionality theorems, we are writing proportions and solving proportions in this lesson. So again, we got to go back to remembering how to make those consistent. And we'll see that again, where we have to definitely make them in a certain way where they work for us. But first, let's get into just a quick little Garfield cartoon where he's looks like playing fetch with Odie. He fetched the ball, Odie, as he throws the ball, and he's waiting for him, and Odie brings back a football. And Garfield says, "Where'd you get that?" And obviously, a second later, he's going to get demolished by the football team right behind him. Okay, so going on into these proportionality theorems. So the first ones here are the triangle proportionality theorem and then the converse of that. So basically what this is saying is if we have a triangle here and we have a line, like this TU line right here, that's parallel to one of the sides. So if a line parallel to one side of a triangle intersects the other two sides, so this line is parallel to one of the sides that QS is parallel to, and it's intersecting the two other sides here, then that divides the two sides proportionally. So right here we could see that's going to divide this proportionally. We could see it dividing it proportionally the way that it's showing you here with RT and TQ, so that would be these two up here. So this one, this little segment right here over the QT segment is going to be equal to the RU segment on this side over the US segment here. Now the converse would just be like the reverse of that, remember? So basically if we have it shown that in a triangle, this segment here, if we're trying to figure out that this is parallel to this QS side, well, if we know from this triangle that these are proportional, so that means that this ratio on the top from this one, so like the RT over the TQ, is equal to the ratio of this one here. Then we know that these lines are parallel. Our TU is going to be parallel to our QS line. Alright, so let's get into a couple of problems that we'll use this proportionality theorem with. Okay, so on page 239, the very bottom page of that page, we see the extra practice for 1 and 2, and we're trying to find the length of AB. So first let's locate where AB is. A is this corner point, B is this point right here on the side. So we're looking for this piece right here. What is the length of A to B? And we're shown some numbers for these other segments in here. So what we also see in this triangle here is these parallel marks. These parallel marks make it to where we know that if these are parallel, then we know these are proportional. So we're proportional here and with these numbers here. So we can set up a proportion with x and 6 so that we can make a ratio out of that. So x over 6. We could start with that, making that ratio, and it's equal to 5 over 10. And here's where we got to make sure we are consistent. So my first fraction here, my first ratio, comes from the same side of this triangle, and the second one comes from the same side. 5 and 10 are on the same side of that triangle as well. So that's consistent going this direction. The tops here come from the same piece from the corner to the first line mark, really basically to this first parallel mark. They're from the same piece on the top. The bottom ones here are from the next ones, from this parallel mark to the next parallel mark. 6 and the 10 come from that one. So you have to make sure that our proportion is set up consistently. And then just cross multiply here to solve for x. So 10x now equals 30. And then divide by 10 so we can see that x is equal to 3. And so we could say that AB is equal to 3. So the length of AB is 3. Number 2, we're looking for AB, which is here. So we want to locate that first. So we're looking for this little segment here. Again, we can set up our proportion. So this side right here with x and 7. X over 7 could be our first ratio. And then the other one will be from the 2 and the 9 down here. We got to put 2 on the top though, because it's going to come from the same piece like the x came from. So it'll be equal to 2/9. That way we're consistent. The fractions are from the same sides, and then the numerators are from this piece, the denominators are from this piece. And then just cross multiply again. So we have a 9x is equal to a 14, and then when we divide by 9, we're just going to get 14 divided by 9, and since that cannot be reduced, we're going to leave our answer that way as an improper fraction. So AB, the length of AB is just going to be 14/9. Okay, here's an example from the book, but this is going to use the converse of that triangle proportionality theorem. So it's got this shoe rack here. It's on the shoe rack. We're showing some triangles for the shoe rack, and we got this line BD right here to kind of cut that there. So we're looking at this triangle right here with A, B, C, D, and E. So BA is 33. So the BA right here is 33. CB is 27. So that's this one up here. We got four things shown to us. CD over here on this side is 44, and the DE down here is 25. So we have all four from two sides. We want to see, are these lines parallel? So it says explain why the shelf is not parallel to the floor. So why is this shelf here, which is where BD is, explain why it's not parallel to AE down here. So what we're going to do is set up a proportion kind of for this with our numbers. So the first proportion we'll do would be the CD and the DE. So you're using this side right here. CD was the 44, the DE was 25. So there's that proportion. The next proportion we'll do would be the other one on this side, so CB and the BA. So it's going to be 27 over 33. So they are being consistent. You know, each fraction is coming from the side, and the numerators are going to be coming from the top section, and the denominators are coming from the bottom section. So they are being consistent, and they got 44 over 25, and this one simplifies to 9/11ths, and you can see, well, those are not equal to each other. So since these are not equal, they're not proportional, that means that the segment here BD is not going to be parallel to AE. Okay, so on the top of 240, you turn your page over to 240. We'll see 3 and 4, and essentially we're doing the same thing as we just saw there. We're trying to determine basically whether AB is parallel to XY. So the AB segment going across here in the middle, if that is parallel down to here, so we want to set up proportions and see, or set up ratios and see if they're proportional, see if those ratios equal each other. If they do, then they are parallel. If they don't, then they're not parallel. So starting with number 3 here, we'll start with one side. We'll start with the AZ and the AX. So that's this side over here. So AZ over this piece right here, AX, so it's going to be 3 over 4. So we'll see that's going to be equal 3 over 4. That's as reduced as we can get it. And then the other side we'll do on this side over here with the ZB and the BY. So BZ and BY, that's these two here. And so I'm being consistent with each ratio is each side length, and then the numerators are going to be from the top one, and the denominators will be from the bottom one. So I got 4/5 over here. The BZ is the 4, and the BY is the 5. And we could see, well, 3/4 does not equal 4/5, so these cannot be parallel. So we'd say not parallel for those ones. So number 3 is not parallel. When we come over to number 4, we'll do the same kind of thing here. We'll start with AZ over AX again, just like before. So AZ is 7.5, AX is 5 there. So we put that down, 7.5 over 5. Well, that's not really reduced very well. So let's go ahead and move this decimal over one place, getting 75, and I'll add a 0 down here to keep that equal. We're 50. So we'll actually see 75 over 50 then, and then we could reduce that by 25. And so that's going to give us a 3 over 2. So this side over here reduces down to 3 over 2. Let's go to the other side. Again, BZ over BY. So it's going to be BZ is the 6, the BY is the 4. So it'll be 6 over 4, and we've reduced that down to 3 over 2 also. So since they do equal each other, 3 over 2 equals 3 over 2, we now can say that the AB is parallel to XY. So we could say, yes, they are parallel. That's what it says, determine whether they're parallel. So we could say yes on this one, but no on number 3. Okay, so here's our next theorem called the 3 parallel lines theorem. So as you can see on the diagram, we have 3 parallel lines right here with those 3 parallel marks, and they're going through 2 other lines here. So it says if 3 parallel lines intersect 2 transversals. Remember, transversal is just going to be a line that's going to go through more than one line. So it's going to intersect 2, so they can be called the transversal. So L and M are going to be our transversals. If that's true, if you have 3 parallel lines intersecting 2 transversals, then they divide the transversals proportionally. And so you could see on this one it says UW, that's this cell segment here, over the WY is going to equal the VX, the same one from here on the numerators, over the XZ, same one on the denominators. So this is on the same fraction or the same ratio. This is the other ratio. Our first piece here is the numerators, the second piece is the denominators, so they are being consistent as they set that up. Another way we could do this as well is actually go from this R all the way over to T. So if I wanted to say maybe the top one again was UW here, and the bottom was VX, because they would have to be consistent. We could then go on this next one, we can write another proportion with UY. We can go from here to here. We could say UY is over VZ. So that could be also something that would work. Okay, so here's another quick book example that helps us use that last theorem with the 3 parallel lines. So it says in the diagram here, angle 1, 2, and 3 right there are all congruent. And then it gives us some numbers for some of these other segments. GF right here is 120. DE over here is 150, and then the DC down here, or CD, is 300. It wants us to find the distance of HF, so from this corner right here all the way up to F up here, this whole segment. We know this is 120, so basically we need to figure out what is this segment here, the H to the G segment, and then add that to 120 to get the full thing. So as we look at this, we know that we don't see the parallel marks. As you notice, those little arrows are not here, but we do see these are all corresponding angles. Corresponding angles being congruent would prove that those are going to be parallel lines. So that proves, because these are corresponding angles, that these are parallel. Corresponding angles are congruent, so we could say that those are all parallel. And that means we can write then a proportion to find the HG. And so that's what they're going to do here using these other 3. We're going to do a little proportion here. So we got the HG one we're trying to find over this one on the same line. And then the DE, that's going to correspond to HG right down here, and it's over the DE, which will correspond to that 120 up there. And so now you fill in the numbers, and we'll just go ahead and cross multiply and solve for HG. So as we cross multiply and solve for HG would be 240, and so now that we know that, we can just say 240 plus 120, that's what we're doing down here, it equals 360, so that whole segment here from H to F then would be 360. Okay, so we'll continue on with the extra practice 5 to 7. It says use the diagram to complete the proportion, and you may want to try this for yourself real quick. You know, this should not be too hard. You can go ahead and pause the video and then just try to fill these in yourself, and then just play it and see if you got them right. So we will be using that, that 3 parallel lines theorem, because we see the parallel lines right here, the parallel marks. These are all parallel to these 2 lines here. And so we can just kind of start setting some things up. So basically we want to get the idea. We're not trying to find necessarily any sides of numbers, but we're trying to be able to set these up in a way that would work for a proportion and make them proportional. So we see we got UV on top of this one, so UV is here, and the corresponding one on the other side is the XY, so that is corresponding to that. Below UV is UW, so U to W. Okay, so on the other side of this one, what's going to correspond to U to W? That's going to be the X to the Z. So that's why XZ is the other corresponding one. So we're just trying to find what's corresponding here. That would correspond. On number 6, we got XY. So XY is here, and then the YZ down here. The other one that's corresponding on this side is the VW. So that's corresponding. What's corresponding to XY is basically just going to be that UV segment right in there. So UV is in there. And then for number 7, we can see on this side we have WU. So W to U is there. We have W to V on the below that. On this side we have Z to Y on the bottom, And so the top is going to have to correspond to W to U. So corresponding to W to U would be Z to X. Z to X. So ZX would be on the top of that proportion. So just trying to get what's proportional, what's corresponding here is really all they want you to try to figure out here as far as completing these proportions, making sure you get things that are corresponding. Okay, here's our joke of the day. What do you call an illegally parked frog? I don't know if you ever thought about that before, but you call it toad. Okay, our last theorem that we're looking at in this section is triangle-angle bisector theorem. Triangle-angle bisector theorem. It's a little bit of a mouthful. So on a triangle, we're bisecting one of the angles that's going to go through the side, or at least connect to the opposite side, and creating two segments over here. And so that's what it's saying. If a ray bisects an angle of a triangle, then it divides the opposite side into segments whose lengths are proportional to the lengths of the other two sides. So here, these are going to be proportional right here to these sides here. So that's where they're showing AD over DB. So that's these two, and one fraction in one ratio is going to be proportional to CA over here over the CB. Notice they're consistent. You have the top side of this ray being the numerators, the bottom side of the ray being the denominators. And this side here where it's using the same side and cutting through it, that's going to be one fraction, and these other two are going to be the other fraction. Okay, we are nearly done, just these last two. So using that last theorem, so that would be the triangle-angle bisector theorem. So we want to find the value of the variable. So they show us a variable here, x, on number 8. What we can see in this diagram is that this line right here is bisecting this angle right here because of these marks being the same. These are both congruent marks, so it's a bisector. And so it is, hitting this opposite side, and it's dividing this opposite side into two other segments. These are proportional now to these other sides here. So we can set up a proportion with x over 5 from this side here. So x over 5. And that's going to be proportional to these 9 and 15. But which one do we put on top? Well, the top's going to be on this side over here of that line because x is on the top. So 9's got to be on the top, and 15 will have to be on the bottom where the 5 was. So it's going to equal 9/15. So now all we have to do to solve for x, cross multiply. So that's going to be 15 times x, 9 times 5. So 15x is equal to 45, and divide by 15. 45 divided by 15, that's easy, just 3. So the value of the variable is 3 for number 8. Now number 9 is a little more challenging because it doesn't necessarily give us, it gives us b right there, but it doesn't give us this piece right here. So here's our bisected segment. There's the angle that's bisecting right there. You can see the two congruent marks showing that this is where it's bisected. Here's the segment that it's cutting into two halves. Here are two parts. B is on one side of this, but it doesn't say what's on the other side like it did here, like it said x and then 5. So if that's the case, it does give us this whole side right here is 14. So what we need to do is say that this piece right here is 14 minus this piece here, which is b. 14 minus b is what this piece is here. So now using that, we can now set up our proportion. So we'll do this 14 minus b over b from this side here. So 14 minus b on the top, b on the bottom. And then using these two numbers, we can make our other ratio. So it's equal to, this will have to be on the top, 6.75 over the 9. That way these two are from the same side of this bisector. Those are going to be our numerators. These are on the other side, the 9 and the b. Those are our denominators. And we can cross multiply. When we multiply 9 times 14 minus b, that's going to require a distributive property. So as we do that, we'll see b times 6.75 is 6.75b, and then 9 goes into here, 126, so 9 times 14 is 126, and then 9 times negative b is negative 9b. We need to get those b's together, so I'm going to add the negative, so the negative 9b, I'm going to add 9b to both sides. Cancels the b's out on the right side, brings them all over here. So that's going to give me a 15.75b is equal to 126. Solving for b, let's divide by 15.75. And here's where you might want to use the calculator, just on 126 divided by 15.75 on the calculator. That's going to give us exactly 8. So you can figure b is 8 on this one. Alright, so that concludes all lessons for Chapter 8. And so you need to go on to Chapter 8.4's assignment and then start getting ready for the quiz. I'll have a quiz on the last 2 lessons here in just a couple days. So I'll see you back in class.